Cylindrical and spherical triple integrals. Let's start with cylindrical. We're going to be looking at solids which are between two surfaces and above a region in the xy plane that is a simple polar region. You could see here in this picture that the equations of the two surfaces are z equals g sub 1 of r theta and z equals g sub 2 of r theta. And we're only looking at the parts of those surfaces that are above the given region. And we see that solid G that is formed there. In this case, to evaluate the triple integral over the solid G of f of r theta z dv, we can change this to an iterated integral by taking the double integral over r of the integral from g1 of r theta to g2 of r theta f of r theta z dz dA. Now, when we change this to a full iterated integral, we get the integral from alpha to beta, the integral from r1 of theta to r2 of theta, the integral from g1 of r theta to g2 of r theta, f of r theta z, r dz dr d theta. The limits on the first two integrals come from exactly the same way you would do it for a double integral. Theta is between alpha and beta, and r is between r1 of theta and r2 of theta. Notice that when we change to the full iterated integral in cylindrical here, an extra factor of r appears inside of the integrand, just like it did when changing to a polar double integral. Let's try an example. Now's a good time to pause the video, try this example yourself, and then resume the video to check your answer with mine. So we have the integral from -2 to 2, integral from negative root 4 minus x squared to root 4 minus x squared, integral from 0 to 4 minus x squared minus y squared, x squared, dz, dy, dx. So first let's draw a picture of the region. Since x is going from -2 to 2, and y is going from negative root 4 minus x squared to y equals root 4 minus x squared, that region looks like a disk of radius 2, centered at the origin, as we could see here. The polar equation of this circle is r equals 2, because it's a circle of radius 2. The solid that we're going to be integrating over has this circle as the region in the xy plane. And notice we're going to be integrating from z equals 0, which is the xy plane, up to z equals 4 minus x squared minus y squared, which is the equation of a parabola that's facing downward and shifted up 4 units from the origin, as we could see here. If we want to convert this equation to cylindrical, then we could change x squared plus y squared to r squared, so that we get z equals 4 minus r squared. Now also, the integrand, x squared, we're going to replace x by r cosine theta so that we get r cosine theta squared. And don't forget that when we change this to a cylindrical triple integral, we're going to throw in an extra factor of r, as we will always do when changing to cylindrical. So writing this as a cylindrical triple integral, theta is going from 0 to 2 pi, r is going from 0 to 2. We could see that from the first picture of the region there. The second picture shows us the z limits. Z is going from z equals 0, the xy plane, straight up until we hit the paraboloid, z equals 4 minus r squared. And then remember that x was r cosine theta, so we get r cosine theta squared times r, which we can multiply out to get r cubed cosine squared theta. Doing the innermost integral, dz, we just get z, because everything in there is constant with respect to z. So we just have r cubed cosine squared theta z from 0 to 4 minus r squared. Substituting in the 4 minus r squared gives us this. Now, to handle that cosine squared theta, we're going to need to use a power reducing formula. We'll rewrite cosine squared theta as 1/2 times 1 plus cosine 2 theta. So we have the integral from 0 to 2 pi, 1/2 1 plus cosine 2 theta d theta, times the integral from 0 to 2, 4r cubed minus r to the 5th dr. Notice that I split this double integral into a product of two separate single definite integrals. I can do that because all of the limits are constant, and the integrand is a function of r times a function of theta. Notice that I replaced cosine squared theta by 1/2 times 1 plus cosine 2 theta using the power reducing formula. And for the dr integral, I just distributed r cubed to the 4 and to the negative r squared to get 4r cubed minus r to the fifth. Integrating each of those, we get 1/2 theta plus 1/2 sine 2 theta, right? 1 becomes theta, and cosine 2 theta becomes 1/2 sine 2 theta. There is a little substitution there. If we let u equal 2 theta, then du is 2 d theta, which is why we need a half to balance that out. For the dr integral, those are just power rules. 4r to the third becomes 4r to the fourth over 4, or r to the fourth, and r to the fifth becomes r to the sixth over 6. Okay, now plugging in the limits. When we plug in a 0 or 2 pi for sine 2 theta, we just get 0. So we just have to plug the 2 pi in for theta to get 2 pi. 1/2 of 2 pi is pi. That's where that first factor comes from. For the second factor there, 2 to the fourth is 16, and 2 to the sixth over 6 is 32 over 3. Getting a common denominator and simplifying this, we get 16 pi over 3 as our final answer. Now let's look at spherical triple integrals. So to change a triple integral to spherical, we're going to rewrite it using an iterated integral with the appropriate limits. In this case, it's best to explain how to get those limits using examples. It's pretty straightforward, but a little complicated to write down in general. And notice that the integrand is f of rho theta phi times rho squared sine phi d rho d phi d theta. An extra factor of rho squared sine phi always appears whenever we change to a spherical triple integral, similarly to how an extra factor of r appears for a polar double integral or a cylindrical triple integral. Just to give an indication as to why that happens, remember that we could think of changing from rectangular to spherical in 2 steps, first going from rectangular to cylindrical and then from cylindrical to spherical. When we go from rectangular to cylindrical, we have to throw in an extra factor of r. When we go from cylindrical to spherical, the analog of throwing in the factor of r from rectangular to cylindrical is throwing in a factor of rho from cylindrical to spherical. So altogether, we have to throw in a factor of r times rho. Now, r is equal to rho sine phi. So rho sine phi times rho is rho squared sine phi. So hopefully this gives you an indication as to why we throw in that extra factor of rho squared sine phi, and maybe it's not so mysterious if you think of it in these 2 steps. But in application, you don't have to understand these steps. All you have to do is throw in a factor of rho squared sine phi anytime you do a spherical triple integral. Let's try an example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Use a triple integral to find the volume of a sphere of radius A. Okay, so here's a picture of a sphere of radius A. I centered it at the origin for convenience. And we're looking for the triple integral over g dv. Notice I don't put anything inside the triple integral, or equivalently, there's a 1 inside there because we're finding a volume. Now, when we change to the spherical triple integral, don't forget to throw in your factor of rho squared sine phi. And we're always going to do it d rho, d phi, d theta in that order, just to be consistent. Now, in this case, theta is going from 0 to 2 pi. You can kind of see that by looking at the circle in the middle of that sphere. We're going to be going around that whole circle to trace out the whole sphere. Phi is going from 0 to pi. Phi is coming from the positive z-axis and coming all the way down past the xy plane and going to the negative z-axis. That will guarantee we get the whole sphere. If we only wanted the upper half of the sphere, we would go from 0 to pi over 2. If we wanted the lower half of the sphere, we would go from pi over 2 to pi. Now, rho is going from 0 to a. It's going from the origin straight out until we hit that sphere of radius a, 0 to a. So this is the triple integral that we want to evaluate. The integral itself is pretty simple. We can do it as a product because all of the limits are constant, and the function inside is a function of rho times a function of phi times a function of theta. Rho squared becomes rho cubed over 3. Sine phi becomes negative cosine phi. And 1, because no factor involving theta appears there, that means it's just 1. So when we integrate 1, it becomes theta. And now when we plug in the limits, we get a cubed over 3 times minus cosine of pi is minus minus 1, or just 1. And the cosine of 0 is also 1. And we're subtracting negative negative 1. So we get 1 plus 1, which is 2. Those signs could be a little confusing, so make sure you write all that down carefully so that you don't make any sign errors. And finally, when we plug in a 2 pi for theta, we get 2 pi. And when we multiply that all together, we get 4 pi a cubed over 3. You may recognize this formula as the standard formula for the volume of a sphere of radius a. Another example. Once again, try this example yourself, pause the video, then when you're done attempting it, resume the video and check your answer. So here we just want to change the given triple integral to a spherical triple integral. So we're not being asked to compute it, just to change it. So we're going to want to start by first drawing a picture of the solid given by this triple integral. Notice it's going to be a simple xy solid because it's of the form dz dy dx. So first of all, the region, x is going from -2 to 2, and y is going from -√4 minus x squared to √4 minus x squared. That's just a disk of radius 2. Now for z is going from z equals 0, that's the xy plane, up until z equals the square root of 4 minus x squared minus y squared. That is the upper half of a sphere of radius 2. There is the picture there. So changing this to spherical, notice that theta is going from 0 to 2 pi. Phi this time is going from 0 to pi over 2. We stop at pi over 2 because it's only the upper half of the sphere. Phi equals 0 is the positive z-axis. Phi equals pi over 2 means we go at a right angle from the positive z-axis, and that is the xy plane. And rho is going from 0 to 2 because it's a sphere of radius 2. Now we replace the z squared by rho cosine phi squared, because z is equal to rho cosine phi. The square root of x squared plus y squared plus z squared is rho. And then we have to throw in our factor of rho squared sine phi, as we always do. And that is now a triple integral in spherical. If we wanted to actually compute this triple integral, we should multiply everything out, and then it's a very, very simple integral. We could do it as a product of 3 single integrals, one a function of rho, one a function of phi, and one a function of theta, just like we did in the last example. But we don't have to actually do it because the question only asked us to change the triple integral to a spherical triple integral and not to evaluate it. One more example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Once again, make sure you draw a picture. This one is a little more challenging than the other two. Find the volume cut from the cone x squared plus y squared minus z squared equals 0 by the sphere x squared plus y squared plus z minus 2 squared equals 4. Here's a picture of that sphere. Notice it's a sphere centered at 0, 0, 2 of radius 2. And here's a picture of our cone, x squared plus y squared minus z squared equals 0. It's our standard cone that's at a 45-degree angle from the positive z-axis. Technically speaking, the cone should have a lower half also, but since the lower half isn't going to touch the sphere, it would just be extra clutter to draw that, so I didn't bother drawing that in. Now, this circle here is the intersection of the cone and the sphere. I'm going to now pull out the important part of the picture here because we're interested in the volume cut from the cone by the sphere. That gives us that picture to the left here. Now I want to change these equations into spherical. So I'm going to multiply out z minus 2 squared. So we get x squared plus y squared plus z squared minus 4z plus 4 equals 4. X squared plus y squared plus z squared is rho squared. The 4's cancel, and bringing the 4z to the other side, we have rho squared equals 4z. Now z, remember, is rho cosine phi. Dividing out a rho on each side of the equation, we have rho equals 4 cosine phi. That is the equation of that sphere in spherical coordinates. Now what about the cone? Getting z squared by itself, we have z squared equals x squared plus y squared. Remember that x squared plus y squared is r squared. We're doing an extra step going to cylindrical. So z is equal to r, or equivalently z over r is equal to 1. Remember that z over r is the tangent of phi, and therefore phi is pi over 4. So we could set up our triple integral in spherical as the integral from 0 to 2 pi. Notice that that red circle is going all the way around. So we're going all the way from 0 to 2 pi with theta. Phi is going from 0 to pi over 4. We're going from the positive z-axis until we hit the edge of the cone, which is phi equals pi over 4. And rho is going from 0 until we hit the sphere. The equation of the sphere is rho equals 4 cosine phi. Then as always, we throw in rho squared sine phi into our integrand, d rho, d phi, d theta. Let's go ahead and evaluate this. Starting with rho, we get rho cubed over 3 from 0 to 4 cosine phi. We leave the sine phi where it is because it's being treated as a constant. Substituting in, we get 4 cubed over 3 times cosine cubed phi, sine phi. 4 cubed is 64. Doing a little substitution here, u equals cosine phi, du equals minus sine phi, d phi. We see that we get negative cosine to the 4th phi over 4 from 0 to pi over 4. So canceling the 4 with the 64, we get negative 16 thirds, the integral from 0 to 2 pi. Cosine 4th pi over 4 minus cosine to the 4th 0 d theta. The cosine of pi over 4 is 1 over root 2. When we raise that to the 4th power, we get 1/4. And the cosine of 0 is 1. When we raise that to the 4th power, we get 1. So we get negative 16 thirds times negative 3/4, which is just 4. And when we integrate from 0 to 2 pi d theta, we just get theta from 0 to 2 pi. So that becomes 4 times 2 pi, which is 8 pi.